So in the last class we have seen what is a tree, right? So a tree will have a root node, then its children and grandchildren, great grandchildren we have seen, and so what is the degree of a tree, what is the height of a tree, so all this we have seen. So I'll just go through quickly, like height. From height I'll go through. So height and depth and number of levels of a tree. So height we are going to represent as what? How many number of levels. So levels we are going to start with what? Level 1 at the root node, then level 2, level 3, level 4 and so on. Right. So for this tree the height is equals to 4. And so what is the degree? So for each node, so there will be a node degree, so that is how many number of children it has. So the root node here, it is having 3 children, so degree is 3. Then here 2, then it is 1, then it is 1, then for manager 0, manager 2 0, manager here 1, and next manager is 0, and work B is 0. So this we have seen in the last class itself. Then what is the tree degree? Tree degree is nothing but the maximum node degree. So here in this tree the maximum node degree is equals to 3. So we are going to take it as what? The tree degree is equals to 3. So degree of this tree is equals to 3. Right? Then now, so we have seen what is a tree. Now our main concept is binary tree. So what is a binary tree? So the name itself, it is saying binary. Binary means what? 2. Right? So binary tree will be having a degree not more than 2. Right? So here what is a binary tree will be defining. Okay, so how it will be and where we are going to use this binary tree and what are the traversal techniques, that all we are going to see in our syllabus. Right? Now coming to binary tree. So what it is a finite, possibly empty. That means what? There is a chance of empty tree also. Okay, binary tree can be an empty tree. Okay, so finite, possibly empty collection of elements. So it will be having some collection of elements. Right? So a non-empty binary tree has a root element. That means if it is non-empty, there will be a root element. Anyhow, binary tree is also a tree, so definitely it will have a root element. The thing is what? If it is non-empty. If it is empty, that means even the root element will not exist. Okay, so non-empty binary tree has a root element. Okay, so the remaining elements are partitioned into 2 binary trees. So the meaning here is the partition into 2 binary trees means 2 subtrees. That means you cannot have more than 2 children at any node. Okay, so if we are taking a root node, for the root node 2 children. Okay, and left is also a binary tree, right is also a binary, so that's a binary tree. So that's why the remaining elements, if you have any elements, then those must be divided into 2 binary trees. Okay, so and that is what these are called, left and right subtrees of binary tree. Okay, so what I told you, if a non-empty binary tree is there, that means there will be a root node. Okay, so the remaining elements, how it will be? It is also a tree, but how many subtrees it should have? Only 2. Right? Left and right subtrees, not more than. But previously if I take, so previous example, if I go through previous example, now you can see here in this tree you have one subtree here, another subtree here, another subtree here at the root node. So root node is having 3 children. Okay, so 3 subtrees are having. But if you go for binary tree, so binary tree will have what? Only 2 subtrees. Okay, left subtree and right subtree. So left and right should also be binary trees. That means left, if we are expanding the tree, it should also have the 2 subtrees. Okay, that means 2 children, not more than 2 children. Right? It cannot have a child also. There may be a possibility. If a node is not having a child, there is a possibility. But the thing is what? It should, if it is having any children, then it should be only 2. not more than 2. Okay, it can be 0, it can be 1, or it can be 2, but not more than 2. Okay, so here you can see the differences between a tree and a binary tree, right? So here, then no node in a binary tree may have a degree more than 2. What I told you? So the degree, what is a degree? Degree is nothing but how many number of children are there for a node, right? So if I am taking a binary tree, no node in a binary tree may have a degree more than 2. That means any node should not contain more than 2 children, right? So it can have 0, or it can have 1, or it can have 2. Okay, what is mean by degree? Degree is nothing but, the node degree is nothing but number of children. So if the number of children are exceeding 2, then it is not said to be a binary tree. Okay, so the restriction here is what? Every node can have maximum 2 children. No node should have more than 2 children. So that is what the main criteria between the difference between a tree and a binary tree. Okay, so binary tree can have only 0 or 1 or 2 children, but tree can have more than 2 children, right? So next difference is a binary tree may be empty. Okay, that means if I am taking nothing, so nothing means what? There is no element. If there is no element also, we can call it as a binary tree. Okay, that means without any node creation. So before the tree creation itself, we can say what? There is a binary tree, but without any elements. Okay, then we can add the elements to expand the tree, right? Then coming to a tree, if I am taking a tree, that cannot be empty. If I am saying it is a binary tree, it can be a empty binary tree. But if you take a tree, it should be some elements there should have, right? So next, the subtrees of binary tree are ordered. Those of tree are not ordered. Okay, so the subtrees, if I am taking binary tree, so those will be what? Ordered. Like if you take A, then it can be B. So next, right? A and B. So these are, both are what? The tree system. The different when viewed as binary trees. Okay, so if I am taking these two, right? So a node is there, then we have a child. So this is a binary tree. Okay, not more than 2 children, right? So one child is there, so it is okay. It is a binary tree. Okay. Here also, if I am taking A and B, so A is having a right child. So it is also binary tree. Okay, it is not having left child. But if I am taking these two, if in terms of binary trees, it is what? No, it is very different. Okay, these two are different. If I am taking a tree, okay, so tree is having what? A parent, and it can have number of children. Okay, but binary condition is what? It should have left and right subtree. So when you are constructing a binary tree, do remember one point, that always it will be started from left child onwards. Okay, so first left child will be generated. After completion, then we have to go for the right child. So this, if I am taking into a binary trees concept, so this can be what? Ordered. It is correct. But here, if I am taking no left subtree, but it is having right subtree, but that means what? It is a different one. Okay, right? So you have to understand this point. Order. Okay, first root, then left and right. Okay, so that is what the order. So this is not considered as a binary tree. In the concept of binary trees, it will be taken as what? A tree. Okay, so binary tree must be ordered. Ordered in the sense what? Root, then left, and then right. Okay, but if you are taking a tree, it may not have any order. So if you don't have left child also, you can have right child. So that is the thing you need to understand. Right, then. So when you are taking a tree, so these two are same. But when you are taking into binary trees, these two are what? Different. So that is the point you need to understand. Okay, so and now where we are going to use this binary trees. Okay, so when you want to represent the arithmetic expressions, like how the arithmetic expressions will be, so there is one example here. So a plus b multiplied by C plus D plus E minus F divided by G star H plus 3.25. So to evaluate this expression, generally we'll go for what? Stacks, and use the postfix expression and evaluate the postfix expression. So that the process we are going to do. Okay, but when you go for the binary tree representation, it is easy to perform this arithmetic expression evaluations. Okay, so how it will be? Right, so this expression, what it is consisting of? It consisting of number of operators, then the operands, right, and some delimiters. Right, so delimiters are what? Here I am taking to represent the operators and operands. I am representing a comma as the delimiter and also the bracket. So open bracket and close bracket. So this is what delimiter in the expression, right? Open bracket and close bracket, that is what the delimiter. Plus, minus, divided by, and multiplication are the operators. A, B, C, D up to these are all what? Operands. Okay, why I am taking this A plus B is also an operand? Because these are in the delimiters and this is first calculated and then this is calculated, and whatever the result is there we have to multiply with this, right? So this is what how the expression will be. So these expressions we can represent in terms of binary tree, how it will be. Now let us take one simple example, A plus B. So generally to perform this expression, to evaluate this expression, we'll go for postfix expression. Already it has been completed expression evaluation in the previous units. Okay, so I'm not going through the expression evaluation. So now how do we represent the binary tree format? Right, so like if you take A plus B, how do I represent in the binary tree? So operand A, operand B, so that has to be added. Right, so A plus B. So how we are taking left operand and right operand will be summed. So that result will be what? Stored here. So that is what binary tree form, how I am representing this simple expression A plus B. So if I am going for minus A, so how do I represent minus A? So that is negative value of A we are going to get, right? So and now if you take this particular expression, a long expression I have taken, so how it will be? So to represent this we are using this binary tree. So from where we are going to start? So A plus B. So this result has to be multiplied with C minus D, right? So that is A plus B, C minus D. So this result and this result is applied to what? Multiplication operation. So here we are going to perform multiplication. So this result we are going to divide with E plus F. So E plus F should be at the right side and plus operation. So E plus F, this result and the result here, so this will be divided. So how we are going to identify this? So which one has to be done first? So generally if you are taking the operator precedence, okay, so that is what, which operation has to be performed first. Now how in this expression if I take A plus B, C minus D, E plus F. So operator precedence, plus and minus will be having equal preference, and the thing here is what? A plus B is enclosed in the brackets, C minus D is enclosed in the brackets, and that result we are supplying toward star. Okay, so even though the star is having highest precedence in the operators, but this brackets will have more precedence because as those are in the brackets, so these will have to be performed first, right? So A plus B and C minus D. So for this operand, the left operand is what? A plus B, right operand is C minus D. Okay, for the star, right? So left operand, here A plus B result should be there, and right operand C minus D result should be there. So left subtree is what? A plus B, right subtree is what? C minus D. Right, so left subtree if I am taking, so left subtree again I have the operator, So operator will be what here, my note, and operands. So what are the operands? A plus B. So A is the left operand and B is the right operand. So A plus B we are going to perform. So this is what the left subtree of star. Okay, the right subtree of star is what? C minus D. Okay, so for C and D the operator is what? Minus. So for this minus operator, the left operand is C, right operand is D. Okay, so this is the left subtree of minus and right subtree of minus. So like this, so 2 we are going to take A plus B, that is what added, and the result is supplied here. C minus D, the subtraction is performed and that result is supplied here. Now these two are, whatever the results are there, that will be multiplied and that will be supplied here. Okay, but to perform this operation, the resultant of right subtree I have to get. So what is the resultant? So if I am taking this divided by, so the left part is what? This subtree, right? So that is the complete this subtree, and right operand, this is what, if I am taking this completely as the left operand, and this is what? Completely right operand. So this is left operand and right operand. So left operand is also a subtree, right operand is also a subtree. Okay, so we are going to perform the division on the left and right subtrees. So what is the right subtree? E plus F. Again it is what? A binary tree where the plus operator has two subtrees. So left operand and right operands. Again we don't have any other operation, so we are not expanding. So we are going to take E plus F and perform the division, right? So this is how the binary tree format of the expression we can represent. So when you are representing in this form, it is easy to understand which has to be performed and how the evaluation expression can be evaluated. So this is what the binary tree representation. Okay, so what is the merits if I am representing in this way? Okay, left and right operands are easy to visualize, yes or not? So if I am taking the division, what are the left operand? Left operand is a subtree, right operand is also a subtree. Okay, so for this subtree, so for star, left operand is what? A plus B, right operand is what? C minus D. So it is easy to understand, yes or not? For plus here, left operand is A, right operand is B, right? For here, minus, left operand is C, right operand is D. For this plus, left operand is E and right operand is F. So it is easy to visualize. And code optimization algorithms work with the binary tree form of an expression. So when you go for expression evaluation, binary tree representation is better to use, right? So simple recursive evaluation of expression instead of going for the long steps of postfix evaluation. So this is very simple to evaluate. So as I told you earlier, right? So this is about how the binary tree is used and what is a binary tree, right? So how we are going to use in the expression representation and expression evaluation. So in the next class we'll see about what are the properties of a binary tree, what are the complete trees and all. So that we'll see in the next class. Thank you.